Acid-base titrations. This is the second of two videos I'm doing on this topic. The first was on pH curves. I would suggest you take a look at that one first. Here we're looking at the choice of indicator, the nature of indicators, and the choice of indicator for any titration. Indicators indicate the endpoint in a titration. I like to think that's how they got their name. Indicators themselves are weak acids or weak bases, and for any indicator, the conjugate acid-base pairs have different colors. To choose an indicator for a titration, we need to predict the equivalence point in the titration and know the endpoint range of the indicator. There's a relationship between the pH range of an indicator and its pKa or pKb value. pH range covers the pH values over which the indicator changes color. The color of an indicator depends on the equilibrium position for its dissociation. Ions have a different color than the parent molecule. Taking litmus, a weak acid, as an example. The undissociated acid represented by HLIT is red. When it dissociates, it forms a conjugate base, LIT-, which is blue. We can write the equation for Ka of the weak acid. Product of the concentrations of the ions formed on dissociation divided by the concentration of the undissociated acid. Adding hydrogen ions drives the equilibrium to the left. The color of the indicator is red in acid. If I increase the concentration of H+, my equilibrium will naturally shift to the left, giving a red color. Adding OH- ions removes H+ and drives the equilibrium to the right. The color is blue in alkali. At the endpoint of the indicator, the concentration of HLIT and LIT- are equal, and the color is purple, a mixture of red and blue. When this happens, Ka equals the concentration of hydrogen ions I see in my equation. Concentration of LIT- and HLIT cancel. And if Ka equals H+, I can say pKa equals pH. The pKa of the indicator gives the pH at which it indicates neutrality. The endpoint of a titration is the point where the indicator changes color and is measured experimentally. The equivalence point is when stoichiometric equivalent amounts of acid and alkali have been added, and it can be calculated theoretically. The correct choice of indicator depends on the rapid change in pH at the equivalence point and the pKa of the indicator. So I've got four possibilities in any titration. The acid could be strong or weak, the alkali strong or weak. Typical pH of the acid, if I take my strong acid, strong alkali, 0 for the acid perhaps, 14 for the alkali. pH at the equivalence point, we'd expect it to be somewhere in the middle, pH 7, and my rapid change of pH over the set of values from 3 to 11. Another example, if I take a weak acid against strong alkali, maybe my acid has a pH around 4, my alkali 14. pH at the equivalence point, let's say 9, somewhere around 9. And the rapid change in pH over the set of values 6 to 11. If the rapid change in pH for the four different types of titration doesn't make perfect sense, I suggest you check out the video on pH curves. Now, two indicators, methyl orange and phenolphthalein. And what I've done is to take my 4 possibilities for a titration and the rapid change in pH that we would expect. Looking at those 2 indicators, different pKa values and different ranges over which they show their endpoint color. Either indicator, in fact any indicator, could be used for titrating a strong acid against a strong alkali. My change in pH values, 3 to 11, is covered by the range over which the indicator shows its endpoint. Only methyl orange could be chosen for strong acid against weak alkali. If I look at my strong acid against weak alkali, I've got my rapid change in pH, and only methyl orange would show its endpoint color within that range. Only phenolphthalein could be chosen for weak acid against strong alkali. That would give me a rapid pH change over a range around 6 to 11. Phenolphthalein shows its endpoint color within that range. Methyl orange is no good. We would never use methyl orange when titrating a weak acid against a strong alkali. We would never use phenolphthalein when titrating a weak alkali against a strong acid. 2 questions to end with, based on questions I've seen in past papers over the years. Take a moment, I'll go through and explain. Well, for A, an indicator is a weak acid and its dissociation is shown in the equation. The indicator is blue in alkali conditions, or the indicator is blue in acidic conditions. Well, in alkali conditions, H plus would be removed and the equilibrium would shift to the right to give the blue color. If you like, alkali would remove H plus and drive the equilibrium to the right. A is good. Concentration of H in and the concentration of ion minus are equal at the equivalence point. One is not greater than the other. Choice A. For 2, the indicator with which pKa would be best choice in titrating a weak base, ammonia, against hydrochloric acid, a strong acid. My change in pH would be approximately equal from 9 to 1, with an equivalence point around pH 5. Best choice, A. That's it. If you got anything from that, please hit like. Please subscribe to be informed of more content.